In this video, I'm going to attempt to show you that any two triangles that have exactly the same edges, the edges of length A, B and C, they must be exactly the same size and their corresponding angles must have exactly the same value. I'll give a disclaimer, which is that as usual, there are many ways to prove the same thing. And there's likely a much easier way to prove this. I'm showing this proof purely because I think it's an interesting one and because I think it's a fairly decent visual representation of how to prove this property of triangles. So let's begin the proof. Let's begin with one line that represents the base edge of the triangle, and let's highlight each end of this edge. And now I'm going to draw two other lines, one joined to the left end of this base and another joined to the right end. In order to form a triangle, the free end of the two lines that we just added need to be joined together, and then the green line would be the left edge of the triangle and the yellow line would be the right edge. I'm going to represent the length of each of these lines with a letter. We'll say the length of the green line is A, and the length of the yellow line is B, and the length of the base is C, so that when we join the free ends of the lines A and B, we'll have a triangle with edges of length A, B and C. Now, because these two lines are joined to the ends of the C edge, we could have the free end of each line in many different positions simply by changing the angle between the edge C and the line. The angle could be anywhere between 0 and 360 degrees, and each of the different angles would place the free end of the line A in a different position. Here are a few examples. Since the line is always attached to the left end of the C edge, the distance to the free edge from the end of C will always be A. And we can represent all of the possible points for the free end of A with a circle. As you can see, whichever angle we use, the free end of the green line is always touching the circle's edge. And we can repeat the same process for the yellow line, which is attached to the right end of the C edge. Here's what we get by rotating the line to a few different angles. And again, we could represent all the possible points for the free end of the B line with a circle. Again, wherever you rotate the line B, the free end is touching the edge of the circle. Now you should be able to see from this setup that there are very few angles which will allow us to create a triangle out of the lines A, B and C. Remember that in order to create a triangle, the free end of A and the free end of B must be in exactly the same position so that they are joined. And we can see that out of all of the possible positions for the free end of A and for the free end of B, there are only 2 points where that occurs. And that is where the circles representing all of the possible points for each free end intersect. And there's one point here and the other point is below the C edge. Now let's rotate the lines A and B so that both of their free ends are touching this point. Now we know that only one angle allows the free end of the A line to be at the point where the two circles intersect. Let's call the angle capital A. The same is true for the line B. Only one angle allows the free end to be at the point where the two circles intersect. Let's call that angle B. Now if we change the angle A or the angle B, it will break the connection between these two endpoints and we no longer have a triangle. So in order to have a triangle with edges A, B and C, we must have these exact angles in these positions, which means that all triangles with the lengths A, B and C must be the same triangle. But to really drive the point home, some of you might be looking at this second point where the two circles intersect. You might be thinking that if we join two other edges from the base to this intersection point, we may not necessarily get a triangle with exactly the same angles. But I'm going to show you why this is exactly the same triangle. Let's add in two new lines to join the ends of the base C to this lower intersection point. And we'll add in the two unknown angles in the upside down triangle. Now we know that these two circles represent every possible position that the ends of the edges A and B can sit at, depending on the angle between the base and the edge. That has to mean that the edge of the circle must always be exactly the same distance from the end of the base edge that's inside it. The distance from the edge of the left circle to the left end of the base edge is A, and the distance from the edge of the circle on the right to the right hand end of the base edge must be B. and that has to mean the left end of the base must be in the center of the left circle and the right end of the base must be at the center of the right circle, and therefore the radius of the left circle must be A and the radius of the right circle must be B. Now if we look at the non-base edges of the bottom triangle, the edge goes from the center of the left circle to the edge of the left circle. Its length is that of the radius, so its length has to be A. And for the right edge of the same triangle, it begins at the center of the right hand side circle and ends at the edge of that circle, so its length must be B. So clearly we have two triangles with edges A, B and C. They share the base, which is C, and they both have sides A and B. We just have to prove that the base angles are of the same value of the other triangle and in the same positions as the other triangle. I'm now going to do a little trick to prove that the triangles are identical. Let's first get rid of the two circles. I'm going to add the top angle in the upper triangle and give it the value of capital C. So the angles in the top triangle are A, B and C, and that means that A plus B plus C must be equal to 180 degrees. I'm going to flip the bottom triangle horizontally so that the edge A is on the right and the edge B is on the left. And now that the edges are flipped positions, you'll notice that opposite edges are the same length. By flipping the bottom triangle, we've created a different shape. It's a quadrilateral, and hopefully you know that the definition of a quadrilateral that has opposite ends that are equal is a parallelogram. But another property of a parallelogram is that adjacent angles are supplementary. That is, the sum of the angles add up to 180 degrees. If we look at the top and the left angle of this parallelogram, they are adjacent angles. The left angle is just a composite angle made up of A and an unknown angle. But because adjacent angles in a parallelogram add up to 180 degrees, A plus the unknown angle plus C must add up to 180 degrees. But if we compare this equation to the original result, you can clearly see that the unknown angle must have the value of B because A plus B plus C equals 180. So the first unknown angle has the value of capital B, and that means that the left-hand angle in this parallelogram has the value capital A plus capital B. And another property in parallelograms is that opposite angles have the same value. So the angle on the right must have the value A plus B, which means that the unknown angle must have the value of capital A. And so the value of both angles is A plus B. And now let's flip the horizontal triangle again back to its original position. And since A plus B plus C equals 180 degrees, the remaining angle in the bottom triangle must have the value of capital C. These two triangles are just a reflection of one another, and hence they are identical. And if we bring our circles back in, you can see that in a triangle of edges A, B and C, there are only two possible points where the edges A and B are able to join. And for both these 2 points, the triangles are identical. So any triangle with edges of length A, B and C is simply a duplicate of the only possible triangle having those edges. And in that way, we've shown that any two triangles that have edges of exactly the same length must have corresponding angles of the same value and are therefore congruent. Well, that's it for now. Thanks for watching.